Okay, so we are in Chapter 4 of An Introduction to Statistical Learning in the second edition. We are on Chapter 4, Question 4. And this one is a doozy, but I think we can get through it all pretty well. So let me start by reading here. So, when the number of features P is large, there tends to be a deterioration in the performance of things like K nearest neighbors or other local approaches that perform prediction using only observations that are near the test observation for which the prediction must be made. This phenomenon is known as the curse of dimensionality, and it ties into the fact that non-parametric approaches often perform poorly when P is large. We'll now investigate this curse. Okay, so here's part A. Okay, so suppose that we have a set of observations, each with measurements of P equals 1 feature, and we're calling that X. We assume that X is uniformly distributed over the interval 0 to 1. Associated with each observation is a response value. Suppose that we wish to predict a test observation's response using only observations that are within 10% of the range of X closest to that test observation. For instance, in order to predict a response for a test observation with X equals 0.6, we will use observations in the range of 0.55 to 0.65. On average, what fraction of the available observations will we use to make the predictions? Okay, so here we have our answer to A. Let me make that a surprise here in a second. Okay, so this part is straightforward. Okay, so let's call the point 1, right? We'll call that R of X. Okay, this is the proportion of X that we're trying to capture around some value. Okay, and in this case it's what was it, 0.6. Okay, so since X represents all of our data, in this case we just have one variable and it is X, well then the amount of available observations that we have to us within 10% of whatever value is 10%. So let's call the proportion of available data A of X. Okay, so here we have that A of X is R of X, right? The amount that we have available to us that's within 10% of our criteria, okay, is just R of X. Okay, so we can simulate this. Okay, so I'm going to simulate what was described. So I'm going to use 100 observations with an R of X of 0.1, right? So 10% of values within X, within an interval. Okay, so now I have my X. So it's just a random uniform distribution. I have n samples from it that go from 0 to 1. And then I'm going to estimate A, so it's the number of observations that we have in our simulation that fall between 0.55 and 0.65. And then I will also count the number of observations that are within that interval, right? So A is a percentage, and N is the actual number of observations that fall within the interval. Okay, so when I run this, okay, so here's X1 along the X-axis. And each one of these little tick marks is a data point, okay? And so we see that as we go along here, we have all of our data points. And now these vertical lines are within 10% of, well, they're actually within 5% of 0.6, right? 5% on either side of 0.6, okay? And so within that interval, we can count the little tick marks. And what we have is that there's 7 observations that fall within that interval. Okay, so 7%, A equals 7%. All right, good. Okay, now part B, suppose that we have a set of observations, but now we have 2 features instead of just 1. So we have X1 and X2. Again, X1 and X2 are both uniformly distributed on 0 to 1 intervals, and they're independent of one another. Okay, so we wish to test test observations response using only observations that are within 10% of X1 and 10% of X2, okay, closest to the test observation. Okay, so for instance, in order to predict the response for a test observation, X1 is 0.6 and X2 is 0.35, we will use observations in the range of 0.55 to 65 for X1 and then 0.3 to 0.4 for X2. On average, what fraction of the available observations will we use to make the prediction? Okay, so let's go down to B. Okay, let me get rid of this here for a second. Okay, so here's B. And instead of trying to figure it out mathematically, let's start by simulating and then figure out the math. Okay, so again, I have 100 observations. I have X1 and X2. Both are uniform distributions between 0 and 1. Okay, again, I'm going to estimate the percentage of observations available to us, okay? So just like before, but now I have more criteria that my available data has to fit, right? X1 has to be between 0.55 and 0.65, and X2 has to be between 0.3 and 0.4. Okay, and so I divide by 100 to get my percentage, and then the number of observations that fit that right here. Okay, so now I'm going to plot it, and now I have a two-dimensional plot, right? I have X1 on the bottom axis and X2 on the vertical axis. Okay, and so actually what we have in this first run, we have no observations fall within the interval. Now the interval that follows both of the criteria for X1 and X2 is this little square. Okay, so if I run this a few times, this time I got 1, so I got 0, I got 1, I got 0, I got 2, I got 0, I got 2. Okay, so we could keep doing this. Okay, but it seems like we're around 1 in 100 roughly. Okay, so again, you can run this a few times and just see what you get. But what you will find is that we're getting about 1% of the observations. Why 1%? Okay, well, this should make sense. So if we just worried about the restrictions placed on X1, well, we already know that that's 10% of the observations of X1. But now for X2, we only get 10% of the 10%. So we have 10% squared, right? So we have, right? So where are we at here, right? So our the amount that we have available to us in 2 dimensions, given that the X1 and X2 were independent, uniformly distributed, right, is 0.1 times 0.1, 10% times 10%, or 10% squared. Okay, so when we run that, 10% squared is 1%. Okay, now this trend continues for any number of I shouldn't say I mean it is parameters, but any number p of features. Okay, so a to the however many features is just simply r to the power of however many features we're looking at, right? So now in part C, we're asked to talk about what about p equals 100 features? What fraction of available observations will we have to us? Okay, well, so you can imagine if instead, so this is 2 dimensions. We could get a 3rd dimension on there, but now we're talking about 100 dimensions, 100 measurements that we're making. Okay, and so now we're asking how. So whatever we'll call it a hypercube later, but how many observations would we expect to meet the criteria for all 100 measurements? Okay, well, using the formula we already found, we'd find that a to the 100 is 0.1 to the 100, right? So you can try to do that calculation, but it's basically 0. So that means with a lot of features, there's going to be less and less data available to us to make our inferences. Okay, so that's what part D is getting at. So part D says, using your answers so far, argue that a drawback in something like k nearest neighbors, when p is large, is that there are very few training observations near any given test observation. Well, that's what we've just shown here, right? As we increase the number of observations, those observations become increasingly sparse, such that there isn't many that are going to be quote unquote near in an absolute sense to any given other data point, right? So it becomes harder and harder to make inferences based on these local methods, okay? These non-parametric local methods. Okay, so that's our answer to D. Okay, finally, part E. Now suppose that we wish to make a prediction for a test observation by creating a p-dimensional hypercube centered around the test observation that contains, on average, 10% of the training observations. For p equals 1, 2, 100, what is the length of each side of the hypercube? Comment on your answer. Okay, so what is a hypercube? So a hypercube is just a shape in p-dimensional space. I'll give an example here in a second, where all sides are the same length. Okay, so in our one-dimensional case, right, so the hypercube, there's just one dimension, and so we just have one side, okay, and it's right there. Okay. In 2 dimensions, we have 2 sides, 1, 2. In 3 dimensions, there'd be a 3rd, and by the time we get to 100 dimensions, there's 100 sides, and they're all the same length. Of course, we can't visualize these things, we just treat them as mathematical objects, but but that's the idea. Okay, so so we want to calculate what is the necessary length for to capture 10% of the training observations for p equals 1, 2, 100, and so on. Okay, well, let's kind of walk our way through this. So let's start with p equals 1 dimension. Okay, so I'm going to go back up. Okay, so here we have p equals 1 dimension. Okay, and so so this is our hypercube, right? That interval. And so what is the length of the hypercube? Well, it's just 0.1, right? We want 10% of the observations, right? And our possible values go from 0 to 1. And so the length of that, in order to capture on average 10 observations out of 100, or 10% of the observations, is 0.1. That's the size of that hypercube. Okay. All right. Well, so let's guess at what a formula might be. Okay. So it could be that the length of p, right? So this is just 1 dimension, is just r to the p. This is our guess. It's going to prove to be wrong here in a second, but we'll get there. Okay. So we have 0.1 to the number of parameters. And for the case of 1, that would work. The length of a one-dimensional 1 is r to the 1. 0.1 to the 1 is 0.1. Okay? All right. But now as p increases, our data becomes sparse, which we've already seen, and it becomes sparse like r to the p. So we have to counteract this, right? So to counteract that, we kind of need to do the inverse of this. And so we need to increase L like r to the 1 over p. Okay? So for L, or I'm sorry, for the length for a one-dimensional hypercube is actually 1 over, or r to the 1 over 1, which is the same as r to the p, right? 0.1 to the 1, which is 1, right? That's why we could have been confused that maybe it was this. But as soon as we go to 2 dimensions, we see that we know that we have to get a larger value, right? The length of a 2-dimensional hypercube, in order to capture the same amount of data, has to be bigger than the 1-dimensional hypercube, right? So now if I take r to the 1 over 2 dimensions, that's 0.1 to the 1 over 2 dimensions. So now I see that my length has to be 0.32. So in other words, so once I had 2 dimensions, right? Remember, I was capturing fewer observations. If I wanted to capture the same number of observations as I was in the 1-dimensional case, I'm going to have to increase the size of this square here, okay? To how big? Well, to where each size is 0.32, okay? And if I had 3 dimensions, it'd have to be 0.46, and so on and so forth until I get, now I'm at 100 dimensions, I have 0.98. So in other words, once I get enough dimensions in there, in order to capture this, some number of observations, I have to look at the entire space, or almost the entire space, right? So that means, so this is only 2 dimensions, but let's just imagine that it was 100 dimensions, just a projection of 100 dimensions. Well, that would mean that I would need to capture basically 98% of x1, 98% of x2, 98% of x3, 98% of x4, all the way to 98% of x100. Okay, so I'm having to capture a lot of the space. Okay, so anyway, so let's actually simulate that. Okay, so this is the first simulation that we've already ran a few times. Okay, so I'm going to run this. So I have 100 observations and I have a 10% interval here. Okay, and I'm capturing about 10%, 9% in this case. Okay, but again, we could run this a few times and we'll kind of hover around 10%. All right. So now we're going to expand this to 2 dimensions. Okay. Now we already saw that when we do this, we're capturing fewer observations. Okay. So this is us capturing fewer observations with these, with these narrow intervals here. Okay? And this time we caught 0. This time we caught 1. And again, we expect to catch about 1 on average. So now next, I'm going to expand these intervals to where the length of these intervals is now, what did we calculate? 0.32. Okay. So now I'm calculating intervals for x1 and x2 that are 0.32 in length. Okay. And so that's what's happening here. Okay. And so now let me plot this. So now we have a much bigger interval here. Okay. And if I run this several times, I'm going to catch on average about 10 observations. Okay, about 10%. But in order to get that 10%, in order to get those 10 observations, I had to have a bigger interval that I was searching. Okay. Now we could go another way. Okay. We could, so instead of having a larger search space, right, to find our 10%, what if we just filled that search space in with more data? How much more data would we need going from, say, 1 to 2 dimensions? Okay. So let's think about this here for a second. So say that we have data from a p-dimensional distribution. Okay. Well, then the number of observations that we have available to us, well, actually here, okay. So if this is the percentage of available observations we have to us, well, then the number, right, so that's a percentage. And so if I wanted the number of available observations we have to us, that would be this, right, where I multiply both sides by the total sample, right, the total number of observations, right. So now that's going to give me the observations that are available to me, right, the total number of observations, no longer as a percent. Okay. So now so that's my number of observations with in p dimensions. But now let's say I have another set of data that is in q dimensions, and q can be more or less. Let's just pretend that it's more for now. Okay. What does m need to be, right, so that I get the same number of observations available to me as when I had p dimensions? Okay. And so I'm deriving the answer here, okay, and so we just take the logarithm of both sides and then solve for m, and then we get that the log of m is this guy right here, and then if we exponentiate both sides, we get that m equals this expression right here. Okay, so you can go through that for yourself. But let's just plug in 1 and 2 dimensions with r of 0.1, which is what we've been working with this whole time. Okay, so we have p equals 1 dimension and q equals 2 dimensions. Okay, so if I plug those in, and you can plug those in for yourself, you'll find that the number of observations we need from the q dimensional data is 1,000. If for the p dimensional data we needed 100, we would need 1,000 from the q dimensional distribution. Okay, so that's a 10-fold increase. That's substantial. Okay, this is what the curse of dimensionality is all about. Okay, so let's work on simulating this. So here I have 100 observations with 1 dimension. Okay, so again, if I run this a few times, I should on average get around 10 observations. Okay, right, 8, 11, 15, 16, 10. Okay, so you can run this a bunch of times and it should average out to about 10 observations. Okay, well now we've said that I need probably 1,000 observations from the q dimensional, in this case 2-dimensional set. Okay, so here I have now 1,000 observations, and what we're going to find is that the number of I'm going to change that to m, is that the number of observations that we will have in the interval is going to be about 10 if we run this a bunch of times, right? But now it took me 1,000 observations instead of 100 to get roughly 10 in that little interval, in that interval of the same size, the smaller interval, right? So again, I can run this several times. Okay, and I'll continue. Well, geez, I keep getting the same number there. Okay, this is impressive. Okay, this is there we go. That's okay. I found a little bit of a typo, but now I think I fixed it. Okay, so now we're getting different values for m, again, which is the number of observations that we have in this interval with 1,000 observations. And it should, you do this a bunch of times, and we should come out to about an average of 10.